Tonight, we're going to confront one of the most unsettling facts in all of physics. General relativity is one of the most successful theories ever created. It predicts the bending of light around galaxies. It predicted gravitational waves decades before we detected them. It describes the behavior of black holes with extraordinary precision. But here's what most people don't realize. At the very center of every black hole, this same theory, the one that works so flawlessly everywhere else, completely destroys itself. It doesn't just struggle. It doesn't just get a little fuzzy. It produces answers that are physically meaningless. Infinite density, infinite curvature, values that no instrument could ever measure because they don't describe anything real. The singularity isn't a place where physics gets difficult. It's a place where physics, as we know it, stops working entirely. And understanding why changes everything about how you see the universe. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with gravity. You experience gravity right now. It's holding you to whatever surface you're sitting or standing on. It keeps the moon in orbit around Earth. It keeps Earth in orbit around the sun. It holds galaxies together across distances so vast that light takes thousands of years to cross them. Gravity is the most familiar force in the universe. You felt it every second of your life. But for most of human history, nobody truly understood what gravity actually is. Isaac Newton gave us the first mathematical framework in 1687. His law of universal gravitation stated that every object with mass attracts every other object with mass. The strength of that attraction depends on how much mass the objects have and how far apart they are. Double the distance and the pull drops to 1/4. Triple it and the pull falls to 1/9. The equation was elegant and it worked beautifully. It explained why apples fall from trees. It explained the orbits of planets around the sun. It allowed astronomers to predict exactly where a planet would be decades into the future. Newton's description of gravity dominated physics for more than 2 centuries. Engineers used it. Astronomers relied on it. It was one of the most successful scientific models ever created. But Newton himself admitted something strange about his own theory. He described what gravity does, not what gravity is. In Newton's model, gravity was an invisible force that acted instantly across empty space. The sun pulls on Earth. Earth pulls on the moon. But how? Through what mechanism? How does the sun, sitting 93 million miles away, reach out across empty space and tug on our planet? Newton called this action at a distance, and he was deeply uncomfortable with it. He once wrote that the idea of gravity acting through a vacuum without any medium was so absurd that no person with a competent faculty of thinking could ever fall into it. He knew something was missing. He just couldn't figure out what. For over 200 years, nobody could. Gravity remained a mystery wrapped in a successful equation. It gave the right answers, but nobody understood the underlying mechanism. Then, in the early 20th century, a young physicist named Albert Einstein changed everything. Einstein didn't just tweak Newton's equations, he replaced the entire framework. He reimagined what gravity is at the most fundamental level. And the picture he revealed is one of the most beautiful ideas in the history of science. Einstein began with a simple observation that turned out to be extraordinarily deep. If you're inside an elevator with no windows, and that elevator is accelerating upward through empty space, you would feel pressed against the floor. You'd feel weight. Objects you dropped would fall to the floor. Everything would behave exactly as if you were standing on the surface of a planet with gravity pulling you down. You could not tell the difference. No experiment you could perform inside that sealed elevator would distinguish between gravitational pull and the acceleration of the elevator. Einstein realized that this wasn't a coincidence. Gravity and acceleration are fundamentally the same thing. This insight, which he called the equivalence principle, became the foundation of his general theory of relativity, published in 1915. Here is what Einstein proposed. Mass and energy don't exert a mysterious force across empty space. Instead, they curve the fabric of space and time itself. Space and time aren't just an empty stage on which events happen. They form a dynamic, flexible structure that can bend, stretch, and warp in response to the presence of mass and energy. What we experience as gravity isn't a force pulling us downward. It's the curvature of spacetime guiding our motion. Think of it this way. Imagine a flat rubber sheet stretched tight. Now place a heavy bowling ball in the center. The sheet deforms. It curves downward around the bowling ball. If you now roll a marble across that sheet, the marble won't travel in a straight line. It will curve toward the bowling ball, following the shape of the deformed sheet. To someone watching from far away, it might look like the bowling ball is pulling the marble toward it. But the marble isn't being pulled by any force. It's simply following the curved surface. This is a rough analogy for how gravity works in Einstein's theory. The sun curves the space-time around it. Earth isn't being pulled toward the sun by an invisible rope. Earth is moving through curved space-time, and the curvature guides it into an orbit. The Moon orbits Earth for the same reason. Earth's mass curves the space-time in its vicinity, and the Moon follows that curvature. Every object with mass or energy warps the geometry of space and time around it, and every other object responds to that warped geometry. Mass tells space-time how to curve. Space-time tells objects how to move. The mathematics behind this are extraordinarily complex. Einstein spent nearly 10 years developing the equations, working through some of the most difficult mathematical structures ever applied to physics. The result was a set of equations now called Einstein's field equations. These equations relate the distribution of mass and energy in a region to the curvature of spacetime in that region. They are beautiful. They are compact when written in the right mathematical language. And they have turned out to be spectacularly, almost unreasonably accurate. Here is why this matters for our story. When a theory makes predictions that keep being confirmed decade after decade, experiment after experiment, that theory earns trust. And general relativity has earned more trust than almost any theory in the history of science. Let me walk you through some of the most important confirmations, because understanding how well this theory works everywhere else is essential to understanding why its failure at one specific place is so disturbing. The first confirmation came before the theory was even published. For decades, astronomers had noticed something odd about Mercury's orbit. Mercury doesn't orbit the Sun in a perfect, fixed ellipse. Its orbit slowly rotates over time, a phenomenon called precession. Most of this precession was explained by the gravitational pull of other planets tugging on Mercury as it orbited. But after accounting for all the known planets, there was a tiny leftover amount. Mercury's orbit was precessing slightly more than Newton's theory predicted, by about 43 arcseconds per century. That's a tiny angle, incredibly small. But it was real, and it was consistent, and Newtonian gravity couldn't explain it. Astronomers spent decades trying to find the cause. Some proposed a hidden planet closer to the Sun than Mercury, a hypothetical world they named Vulcan. Others suggested the Sun wasn't perfectly spherical. Nothing worked. When Einstein applied his new equations to Mercury's orbit, the extra precession appeared naturally. No hidden planets, no special adjustments. The equations simply predicted 43 arc-seconds per century of additional precession, exactly matching the observed value. Einstein later said that when he saw this result, his heart literally raced. He knew he was onto something real. The second great confirmation came in 1919. Einstein's equations predicted that light should bend when it passes near a massive object, because the object curves spacetime, and light follows that curved geometry. During a total solar eclipse, the British astronomer Arthur Eddington led an expedition to measure the positions of stars visible near the edge of the Sun. If general relativity was correct, starlight passing close to the Sun should be deflected, making the stars appear slightly shifted from their normal positions. Eddington's measurements confirmed the predicted deflection. The results matched Einstein's prediction, not Newton's. This was front-page news around the world. Overnight, Einstein became the most famous scientist alive. General relativity was no longer a mathematical curiosity. It was a confirmed description of reality. Since then, the confirmations have only accumulated. General relativity predicts that time passes at different rates depending on the strength of the gravitational field. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields. This isn't a mechanical effect on the clocks themselves. Time itself passes more slowly in a deeper gravitational well. This has been measured directly. In 1959, physicists Robert Pound and Glenn Rebka measured the difference in the rate of time between the top and bottom of a tower at Harvard University. The tower was only about 74 feet tall. The difference in gravitational strength between the top and bottom was tiny, but using extremely precise measurements of gamma-ray frequencies, they confirmed that time at the bottom of the tower ran slightly slower than time at the top, exactly as Einstein predicted. Today, this effect isn't just a laboratory curiosity. It's something engineers have to account for in everyday technology. The Global Positioning System, the network of satellites that tells your phone where you are, relies on atomic clocks aboard the satellites. Those satellites orbit at about 12,500 miles above Earth's surface, where gravity is weaker than on the ground. Because gravity is weaker up there, time runs faster for the satellites than for clocks on Earth's surface. The difference is tiny, about 38 microseconds per day. But if GPS didn't correct for this, your position would drift by roughly 6 miles every single day. The fact that GPS works, the fact that it accurately locates you on a specific street corner, is direct confirmation that general relativity correctly describes how gravity affects the flow of time. Then there are gravitational waves. Einstein's equations predicted that when massive objects accelerate, they send ripples through space-time itself, like waves spreading across the surface of a pond when you drop a stone. These ripples are gravitational waves, and they travel at the speed of light. For decades, most physicists thought gravitational waves would never be detected directly. They're extraordinarily weak. Even waves generated by cataclysmic events like colliding black holes would stretch and compress space by amounts far smaller than the width of a single atom by the time they reached Earth. Indirect evidence came first. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other at enormous speeds. They catalogued it as PSRB 1913+16. Over years of observation, they found that the orbit was shrinking at exactly the rate general relativity predicted for a system losing energy through gravitational wave emission. This was powerful indirect proof. The system was losing energy, and the only explanation that matched the data was that energy was being carried away as gravitational waves, exactly as Einstein's equations demanded. Hulse and Taylor received the Nobel Prize for this discovery, but the direct detection came in 2015. The LIGO Observatory, a pair of enormous laser instruments in the United States, detected gravitational waves produced by two black holes spiraling into each other and merging roughly 1,300,000,000 light-years away. Each black hole had a mass around 30 times the mass of our Sun. When they collided, the impact released more energy than all the stars in the observable universe were producing at that moment, and that energy radiated outward as gravitational waves. By the time those waves reached Earth, they stretched and compressed the LIGO detector by a distance about 1,000th the width of a proton. And LIGO detected it. The signal matched general relativity's predictions with extraordinary precision. We didn't just detect gravitational waves, we confirmed that even in the most extreme gravitational environments, where space-time is being violently distorted by merging black holes, Einstein's equations hold up perfectly. And then, in 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy M87, a monster with a mass about 6.5 billion times the mass of the Sun. The image showed a bright ring of superheated gas surrounding a dark central region, the shadow of the event horizon. The shape, the size, the brightness profile, all of it matched what general relativity predicted. Once again, Einstein's theory delivered. So, here is where we stand. General relativity has passed every single test we've thrown at it. It explains Mercury's orbit. It predicts the bending of starlight. It correctly describes how gravity affects the flow of time. It predicted gravitational waves decades before we had the technology to detect them, and when we finally did, the signal matched perfectly. It predicted what a black hole's shadow should look like, and when we finally imaged one, the picture matched. This is one of the most battle-tested theories in the entire history of science. And this is precisely what makes what comes next so unsettling. Because general relativity doesn't just describe how gravity works around planets and stars, it also predicts what happens when gravity becomes extreme. When enough mass is compressed into a small enough region, space-time doesn't just curve gently. It curves so severely that it closes in on itself. It creates a region from which nothing, not light, not matter, not information of any kind, can ever escape. This is a black hole. Black holes aren't science fiction. They aren't speculative. They're a direct mathematical consequence of general relativity's equations. In 1916, just months after Einstein published his theory, a German physicist named Karl Schwarzschild found the first exact solution to Einstein's field equations. He did this while serving on the Eastern Front during the First World War, working through the mathematics in the trenches. His solution described the space-time geometry around a perfectly spherical, non-rotating mass. And it revealed something remarkable. If that mass were compressed below a certain critical radius, space-time would curve so drastically that a boundary would form. Beyond that boundary, escape becomes impossible. That critical radius is now called the Schwarzschild radius. That boundary is the event horizon. For decades, many physicists, including Einstein himself, doubted that such extreme objects could actually form in nature. They thought the singularity was a mathematical curiosity, something that appeared in idealized solutions, but would be avoided by the messy reality of a real collapsing star. A real star isn't a perfect sphere. It has bumps and irregularities and rotation and internal pressure. Surely these complications would prevent the kind of total collapse that Schwarzschild's solution implied. Surely nature would find a way out. Nature didn't find a way out. In nature, black holes form when massive stars die. A star spends its life in a delicate balance. The outward pressure from nuclear fusion in its core pushes against the inward pull of its own gravity. For millions or billions of years, these two forces balance each other, and the star remains stable. The star burns hydrogen into helium, helium into carbon, carbon into heavier elements, each stage releasing energy that keeps the star inflated against its own weight. But when a sufficiently massive star exhausts its nuclear fuel, that balance breaks. The outward pressure disappears. Gravity wins. And without anything to resist it, gravity crushes the star's core inward with catastrophic force. For stars of moderate mass, the collapse can be halted. A star about the mass of our Sun will eventually collapse into a white dwarf, an object about the size of Earth supported by the quantum mechanical pressure of its electrons. A more massive remnant can collapse further into a neutron star, an extraordinarily dense object only about 12 miles across, supported by the quantum mechanical pressure of its neutrons. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. These are extreme objects, but physics provides a mechanism to halt the collapse at a finite density. But if the remaining core is massive enough, roughly more than about 3 times the mass of our Sun, nothing in the known laws of physics can halt the collapse. Not electron pressure, not neutron pressure, not any known force. The matter falls inward, the curvature of spacetime increases, and an event horizon forms. The object becomes a black hole. Now, here is something crucial that most people misunderstand. The event horizon is not the singularity. These are two very different things, and confusing them leads to confusion about the entire subject. The event horizon is a boundary in spacetime. It marks the point of no return. Once you cross it, you cannot turn back, because doing so would require traveling faster than light, which is impossible. But the event horizon itself is not a physical surface. It's not a wall. It's not a barrier you'd slam into. It's not a membrane or a shell or anything you could touch. An astronaut falling into a sufficiently large black hole would cross the event horizon and, at the moment of crossing, notice nothing unusual at all. Locally, spacetime at the horizon is perfectly smooth. The laws of physics work normally there. You could check your watch. You could look around. You wouldn't feel a sudden jolt or see a flash of light. The crossing would be completely unremarkable from your own perspective. This is a critical point. General relativity has no problem describing spacetime at the event horizon. The equations work there. The curvature is finite. The physics is well defined. An outside observer would see strange things, like light from the falling astronaut becoming increasingly redshifted and dimmer, the astronaut's image appearing to freeze at the horizon's edge, growing fainter and redder until it fades from view. From the outside perspective, the astronaut never quite crosses the horizon. They seem to slow down and fade away. But this is a consequence of how light escapes from near the horizon, not of what's happening to the astronaut. For the astronaut, the crossing happens normally. They pass through and continue falling. The problem lies deeper. Once past the event horizon, general relativity says you have no choice but to continue falling inward. Every possible path through spacetime leads further in. This is perhaps the most disorienting thing about the interior of a black hole. In the universe outside, you have freedom in space. You can move left or right, up or down, toward a star or away from it. Time is the dimension you can't control. You move forward in time whether you like it or not. But inside the event horizon, the roles reverse. The inward direction effectively becomes the future. Just as you can't stop moving forward in time right now, you can't stop moving inward once you've crossed the horizon. The center of the black hole isn't a place in space that you're being pulled toward. It's a moment in your future that you cannot avoid. No matter what you do, no matter which direction you point your rockets, no matter how hard you accelerate, the center of the black hole lies ahead of you in time. You will reach it for the same reason you will reach tomorrow. And as you fall inward, the curvature of spacetime increases. Tidal forces grow stronger. Spacetime warps more and more violently. General relativity's equations describe this process with mathematical precision. They track the curvature increasing, the tidal stretching intensifying, the geometry warping ever more severely. The equations keep running, producing answers at every stage of the infall. At every point along the way, the theory dutifully reports the curvature, the density, the tidal forces. And at every point, those values are larger than the point before. The numbers climb, steadily, relentlessly, without any sign of leveling off. Until they don't level off at all. Because according to those same equations, the ones that have been so spectacularly successful at describing everything else, the curvature doesn't simply get large. It doesn't plateau at some enormous but finite value. It grows without limit. It marches toward infinity. The density of the infalling matter increases without bound. The tidal forces become infinitely strong. Spacetime curvature becomes infinite. All the paths through spacetime converge on a single point, where every physical quantity the theory can calculate is driven to a value that no longer represents anything physically meaningful. This is the singularity. And the singularity is not like any of the other predictions general relativity has made. It's not like the bending of light, which we can measure. It's not like gravitational time dilation, which GPS satellites confirm every day. It's not like gravitational waves, which LIGO detects with breathtaking precision. Those are predictions that describe real physical phenomena in the real universe. The singularity is something else entirely. The singularity is the point where the theory that produced all those confirmed predictions appears to turn against itself. The very equations that work so perfectly to describe black holes from the outside, the same equations that tell us the event horizon exists, that predict its exact size, that describe how light bends around it. Those equations, when pushed to their logical conclusion inside the black hole, produce answers that cannot possibly be right. Infinite density, infinite curvature, physical quantities with no upper bound. This is the paradox at the heart of modern physics. General relativity is arguably the most successful gravitational theory ever conceived. It has never failed a single experimental test. It describes the event horizon with elegant precision. And yet, the moment you follow its own mathematics past that horizon and down toward the center, the theory drives itself into a wall. It produces numbers that don't describe anything real. It predicts its own failure. The question then becomes unavoidable. If general relativity is so accurate everywhere else, why does it break down here? What is actually happening at the center of a black hole? And what does it mean that our best theory of gravity, the one that has passed every test we have ever devised, contains within its own equations a point where it simply stops making physical sense? These questions lead us into the deepest unresolved mystery in all of physics. And answering them is going to require us to look very carefully at what a singularity actually means, why infinite answers aren't predictions but cries for help, and why the center of a black hole might be the most important place in the universe for understanding the true nature of reality. So now we know what general relativity predicts. We know that when a massive enough star dies, gravity crushes the remnant inward until an event horizon forms. We know that the event horizon is a point of no return, but that space-time there is still well behaved. And we know that the equations, when followed inward past the horizon, drive every physical quantity toward infinity. Density, curvature, tidal forces, all of them climbing without bound toward values that don't correspond to anything we can measure or even imagine measuring. But what does this actually mean? What is a singularity, really? This is where most explanations go wrong, because the word itself is misleading. When most people hear the word singularity, they picture something: a tiny ball of infinite density, an infinitely small point containing all the mass of a collapsed star, a physical object that's just extremely, unimaginably compressed. And that picture is wrong. Not slightly wrong, fundamentally wrong. Because a singularity isn't a thing. It isn't an object. It isn't something sitting at the center of a black hole that you could, in principle, reach out and touch if you were somehow indestructible. A singularity is what happens when a mathematical framework is pushed beyond the boundaries of its own validity. It's the equations screaming that they can't handle what's being asked of them. Let me explain this carefully, because it changes everything about how you should think about black holes and about the limits of human knowledge. In mathematics, a singularity is a point where a function, or an equation, ceases to be well defined, where it produces output that is meaningless or undefined. Mathematicians encounter singularities all the time. They're not exotic or mysterious in mathematics. They're diagnostic. They tell you something about the limitations of the tool you're using. Here's the simplest possible example. Take the number 1 and divide it by a number that gets closer and closer to 0. 1 divided by 1 is 1. 1 divided by 1/10 is 10. 1 divided by 1/100th is 100. 1 divided by 1/1,000,000th is 1,000,000. As the number you're dividing by approaches 0, the result grows without limit. And 1 divided by 0 itself is undefined. It's not infinity. Infinity isn't a number you can write down and do arithmetic with. The operation simply doesn't produce a valid answer. The mathematical machinery breaks. That's a singularity. Now, in physics, when the equations describing a physical system produce a singularity, it almost never means that nature itself is doing something infinite. It almost always means that the model you're using has been stretched past the point where it accurately represents reality. The model has hit a wall, and instead of giving you useful information about what's actually happening, it gives you gibberish, infinite values, undefined quantities, nonsense outputs that tell you one thing and one thing only. Your theory is no longer adequate for this situation. This has happened before in the history of physics, and looking at those historical examples helps make the point. Consider classical electromagnetism. In the 19th century, physicists developed an extraordinarily successful mathematical framework describing electric and magnetic fields. It's one of the great achievements of physics. But if you use that framework to calculate the energy contained in the electric field of a single electron, treating the electron as a point particle with no spatial extent, you get infinity. The energy should be the integral of the field energy density over all space. And near a point charge, that integral diverges. It doesn't converge to a finite value. The math says a single electron should contain infinite electromagnetic energy. Obviously, electrons don't contain infinite energy. Electrons are real physical objects. They interact. They have measurable mass. They behave in well-defined, predictable ways. The infinity didn't mean nature was doing something infinite. It meant the model, classical electromagnetism, applied to a point particle, was being used outside its range of validity. The framework was pushing into a regime where its assumptions no longer held. The resolution came with quantum electrodynamics, a deeper theory that handled the situation properly and produced finite answers. The classical singularity was a signpost, not a feature of reality. The same thing happened in fluid dynamics. Classical equations describing fluid flow can produce singularities under certain conditions. The equations might predict infinite velocities or infinite pressures at certain points. But fluids don't actually develop infinite velocity. What happens in reality is that the smooth, continuous description of the fluid breaks down. At some scale, you have to account for the fact that fluids are made of individual molecules, and the continuum approximation fails. The singularity in the equation wasn't describing something physically real. It was telling you that the model had reached the edge of its applicability. The singularity inside a black hole is exactly the same kind of signal, but far more profound. General relativity treats spacetime as a smooth, continuous fabric, a geometric structure that bends and curves in response to mass and energy. And for an astonishing range of conditions, this description is perfect. It works for weak gravitational fields like those around Earth. It works for moderately strong fields like those around neutron stars. It even works at the event horizon of a black hole, where gravity is intense, but space-time curvature is still finite and well-defined. But as you approach the center, the curvature grows without limit, and the theory has no mechanism to stop it. General relativity's equations don't contain any built-in flaw, no minimum distance, no maximum density, no cutoff that prevents the curvature from climbing forever. The equations just keep going, producing ever larger numbers until they reach infinity. And infinity, in physics, is not a valid physical quantity. You cannot have infinite density. There is no instrument that could measure it. There is no physical process that could produce it. Infinity is not a number that appears on any measuring device in any laboratory in the universe. When a physical theory produces an infinite answer, it doesn't mean the universe is doing something infinite. It means the theory has broken. Let me take you through what general relativity actually predicts as you fall toward the singularity, so you can see how the breakdown unfolds. You've crossed the event horizon. As we discussed, space-time at the horizon is still smooth. But now, every path through space-time leads inward. The radial direction is no longer something you can move freely along, choosing to go closer or farther from the center. Inside the horizon, the inward direction has taken on the character of time. Moving toward the center is as inevitable as moving forward into your next moment. You can't turn around for the same reason you can't travel backward in time. As you continue inward, tidal forces begin to grow. Tidal forces are differences in gravitational pull across extended objects. Even outside a black hole, tidal forces exist. The moon's gravity pulls slightly harder on the side of Earth facing the moon than on the far side, which is what creates ocean tides. But near a black hole's center, tidal forces become extreme. The gravitational pull on your feet, if they're closer to the center, becomes dramatically stronger than the pull on your head. You'd be stretched vertically and compressed horizontally. Physicists have a technical term for this. They call it spaghettification, because your body would literally be drawn into a long, thin strand, like a piece of spaghetti. For a stellar mass black hole, one formed from the collapse of a massive star, this spaghettification would actually begin before you even cross the event horizon. The tidal forces would kill you long before you reach the center. But for a supermassive black hole, like the one at the center of the Milky Way, Sagittarius A star, which has a mass about 4 million times that of the Sun, the event horizon is so large that the tidal forces there are actually quite gentle. You could cross the horizon comfortably. The spaghettification would only become lethal much closer to the center. But this isn't just about hypothetical astronauts. Think about what happened to the actual star that formed the black hole. A real star collapsed. Real matter, iron nuclei, neutrons, quarks, an entire stellar core's worth of physical substance fell inward. And according to general relativity, nothing stopped it. The matter passed through every known state. It was compressed past the density of an atomic nucleus, past the density of a neutron star, past the density of any physical state that the standard model of particle physics can describe. Every barrier that physics provides, electron degeneracy pressure, neutron degeneracy pressure, the strong nuclear force holding protons and neutrons together, every one of them was overwhelmed. The matter was driven through all of them and past them all, and general relativity says it kept going. There was no final flaw, no ultimate state of matter where the compression stopped. The density continued to climb without limit. The original star's material, real physical substance with real mass and real energy, was compressed toward a state that no theory of matter can describe. The singularity isn't just a theoretical concern about what would happen if you fell in. It's a statement about what already happened to a real star's worth of matter when the black hole formed. That matter is somewhere. It did something. But general relativity cannot tell us what. And as the tidal forces grow, the situation only worsens. Eventually, no matter the size of the black hole, the tidal forces grow without bound as you approach the center. According to general relativity, they increase without limit. The there's no point at which they level off. They don't reach some large but finite maximum. They climb toward infinity. The stretching force pulling you apart grows infinite. The compression pushing you from the sides grows infinite. Every physical quantity that describes the local geometry of spacetime, quantities that are perfectly finite and well-behaved everywhere else, is driven toward a value that cannot represent anything real. And here is the truly unsettling part. The climb is relentless. The numbers don't hesitate. They don't slow their ascent. There is no ledge on the way down, no plateau where the curvature pauses, no bottleneck where the density reaches some enormous but stable value and stays there. The equations produce a perfectly smooth, perfectly monotonic increase. Every step closer to the center produces a larger value than the step before, and the next step produces a larger one still, and the next, and the next. The theory never says stop. It never says here is the maximum. It just keeps driving the numbers upward, through values that are large, then absurdly large, then incomprehensibly large, and then past anything that words or measurements can capture. The numbers go to infinity, not in a dramatic explosion, but in a cold, steady, mathematical march. The equations run calmly and obediently toward a cliff, and when they reach the edge, they don't stop. They keep calculating, and the answers they produce on the other side mean nothing. And it's not just tidal forces. The curvature of space-time itself, described by mathematical objects called the Riemann curvature tensor and its various contractions, diverges. These curvature quantities encode the full geometric information about how space-time is warped at any given point. They're finite at the event horizon. They're finite everywhere outside the black hole. They're finite everywhere in the universe that we can observe and measure. But at the singularity, they blow up. They become infinite. The geometry of space-time becomes, in a mathematical sense, infinitely distorted. There is another way to see why the singularity represents a breakdown, and this one is especially powerful. It involves a concept called geodesic incompleteness. In general relativity, the paths that objects follow through space-time are called geodesics. A geodesic is the space-time equivalent of a straight line. On a flat surface, the shortest path between 2 points is a straight line. On a curved surface, like the surface of a sphere, the shortest path between 2 points is a curve called a great circle, like the routes airlines fly across the globe. In curved space-time, objects in free fall, objects with no forces acting on them except gravity, follow geodesics. These are the natural paths through curved space-time. In a well-behaved space-time, geodesics can be extended indefinitely. You can trace a path forward and backward in time without it ever ending, or it ends by reaching a boundary of the space-time that makes physical sense. But at the singularity, geodesics terminate. They reach a point and simply stop. They can't be extended any further. The mathematical road through space-time comes to an abrupt end. It doesn't end because the object hit something. There's no wall, no surface, no physical barrier. It ends because the space-time itself ceases to be defined at that point. There is no more space-time to move through. This is geodesic incompleteness, and it's one of the most rigorous ways to define what a singularity actually is. It's not defined by infinite density or infinite curvature, although those often accompany it. It's defined by the fact that space-time itself has an edge, a place where the equations stop providing a description. The fabric of space-time doesn't just curve violently, it ends. An object falling toward the singularity doesn't reach a destination. It reaches the boundary of the theory's ability to describe reality. In 1965, Roger Penrose proved a theorem that shook the foundations of physics. He showed, using rigorous mathematical arguments, that singularity formation is not a quirk of perfectly symmetric, idealized models. It's not something that only happens if a collapsing star is a perfect sphere, with no bumps, no irregularities, no rotation. Penrose proved that under very general conditions, once an event horizon forms, singularity formation is inevitable. It doesn't matter what shape the star had. It doesn't matter how messy the collapse was. It doesn't matter what the internal composition of the matter was. Once enough mass has been compressed past the point of no return, the formation of a singularity is guaranteed by the very structure of general relativity. To understand why this was so important, you need to understand what physicists believed before Penrose. For decades, there had been a hope, almost a faith, that singularities were artifacts of idealization. The earliest solutions to Einstein's equations that contained singularities were all highly symmetric. Schwarzschild's solution described a perfectly spherical, non-rotating mass. Later, Roy Kerr found a solution for a rotating black hole, and it also contained a singularity. But these were mathematically perfect objects. A real collapsing star isn't a perfect sphere. It has convection currents, magnetic fields, asymmetric explosions, jets of material blasting outward. Surely, physicists thought, all that messiness would disrupt the collapse. Surely the matter would find a way to avoid converging on a single point. Surely the singularity was just what happened in the unrealistic limit of perfect symmetry, and real physics would always provide an escape. Penrose destroyed that hope. His theorem didn't depend on symmetry at all. It used a completely different approach, relying on the global causal structure of spacetime rather than the details of any particular solution. He showed that once a trap surface forms, a region where all light rays are being forced inward by the curvature of spacetime, then geodesic incompleteness is guaranteed. Some path through spacetime must end. The details don't matter. The composition of the matter doesn't matter. The symmetry doesn't matter. The singularity is inevitable. It follows from the most basic structural properties of general relativity itself. This was a turning point. Before Penrose, you could reasonably hope that the singularity was a mathematical fantasy. After Penrose, you couldn't. The theorem told physicists that singularities aren't optional. They aren't avoidable. They're a necessary consequence of general relativity, whenever gravity becomes strong enough to form a black hole. The theory doesn't just permit its own failure, it demands it. Shortly after, Stephen Hawking extended Penrose's work, applying similar techniques to the universe as a whole, and showing that the Big Bang itself likely involved a singularity. Together, the Penrose-Hawking singularity theorems established that singularities aren't rare or exotic edge cases. They're endemic to general relativity. They're woven into the theory's mathematical fabric. Under realistic physical conditions, the kind of conditions that actually exist in our universe, general relativity practically demands that singularities form. This is a profound and deeply uncomfortable result. It means that the breakdown isn't a flaw in how we set up the problem. It isn't caused by unrealistic assumptions or oversimplified models. It's built into the theory itself. General relativity contains, within its own structure, the seeds of its own failure. Follow the equations far enough, under conditions that the universe actually produces, and the theory breaks. Penrose received the Nobel Prize in Physics in 2020 for this work, more than 5 decades after the original theorem. The significance of the result only grew with time. And here is another crucial point that doesn't get enough attention. The singularity is not observable. No signal, no light, no information of any kind can travel from the singularity to the outside universe. Everything that crosses the event horizon is permanently cut off from the rest of the cosmos. Whatever is happening at or near the singularity, whatever replaces the infinite values in reality, that information is locked behind the event horizon. We cannot see it. We cannot measure it. We cannot probe it with any instrument we could possibly build, because any instrument that got close enough would itself be trapped behind the horizon, unable to send data back. This means the singularity is fundamentally different from almost every other prediction in physics. When general relativity predicts that light bends around a massive object, we can test that. We can set up an observation and check. When it predicts gravitational waves, we can build a detector and listen. When it predicts the shape of a black hole's shadow, we can construct a planet-spanning telescope array and take a picture. But the singularity hides behind the event horizon. It's a prediction that, by its very nature, cannot be directly tested. Roger Penrose proposed something called cosmic censorship, the conjecture that nature always hides singularities behind event horizons. Every singularity comes wrapped in its own information barrier. If cosmic censorship holds, then no naked singularity, a singularity without an event horizon, can ever form in the real universe. The breakdown is always concealed. The universe, it seems, might be embarrassed by its own contradictions. But think about what it would mean if cosmic censorship failed. If a singularity could form without an event horizon wrapping around it, the breakdown would be exposed. The point where physics produces meaningless infinities would be visible to the outside universe. Signals from the singularity could reach us. Effects from a region where the laws of physics are undefined could propagate outward and influence the rest of the cosmos. The singularity would no longer be a private failure hidden behind a curtain. It would be a public catastrophe, an open wound in spacetime pouring undefined physics into the universe around it. We wouldn't just lose predictability at a single hidden point. We'd lose predictability everywhere the singularity's influence could reach. This is why cosmic censorship matters. It's not just an abstract mathematical conjecture. It's the question of whether the breakdown of physics at the singularity can contaminate the rest of the universe. Most physicists believe it can't. Most believe cosmic censorship holds, at least in its weak form, which states that singularities formed from realistic physical processes are always hidden. But the conjecture remains unproven after more than 50 years. It is one of the great open problems in mathematical physics. But the fact that we can't observe the singularity doesn't mean it doesn't matter. It matters enormously. Because the singularity tells us something profound about the theory that predicted it. It tells us that general relativity, for all its spectacular success, is incomplete. Think about what that means. We have a theory that has been tested more rigorously than perhaps any other theory in science. A theory that has predicted phenomena decades before we had the technology to detect them. A theory that describes the behavior of spacetime from the scale of tabletop experiments to the scale of colliding galaxies. And this theory, when applied to conditions that the universe actually creates, produces answers that are physically meaningless. It doesn't just get slightly inaccurate. It doesn't just lose a little precision. It produces infinity. It stops being able to describe reality altogether. The singularity is a signpost. It's a marker. It says, in the clearest possible mathematical language, that something is missing from our understanding. General relativity is not the final word on gravity. It's an extraordinarily good approximation, possibly the best approximation ever developed in the history of science, but it's still an approximation. There is a deeper theory underneath, a more complete description that takes over where general relativity fails. We don't know what that theory is yet, but we know it must exist, because general relativity itself tells us so. Its own equations point to the place where it breaks down and say there must be something beyond this. Let me offer an analogy that might help clarify why the singularity is a breakdown of the theory rather than a feature of reality. Think about a map projection. If you try to represent the surface of a globe on a flat piece of paper, you inevitably introduce distortions. The Mercator projection, one of the most familiar map projections, works beautifully for most of the globe. It accurately represents shapes and directions at most latitudes. Sailors used it for centuries precisely because it was so reliable for navigation. But near the poles, the Mercator projection fails catastrophically. Greenland appears as large as Africa, even though Africa is actually about 14 times larger. And the North and South poles themselves can't be represented at all. They would be stretched to infinite width. The projection produces a singularity at the poles. Does this mean the poles don't exist? Does it mean there's something wrong with the Earth at the poles? Of course not. The poles are perfectly normal locations on the globe. The problem isn't with the Earth. The problem is with the projection. The mathematical tool being used to represent the surface breaks down at those specific points. To describe the poles properly, you need a different projection, one that handles those regions without distortion. In the same way, the singularity in a black hole might not reflect anything wrong with the universe at the center of the black hole. The problem might be entirely with general relativity, the mathematical framework we're using to describe that region. General relativity might be like the Mercator projection. Brilliant, extraordinarily useful, accurate across a vast range of conditions, but fundamentally unable to handle one specific regime. To describe what actually happens where general relativity predicts a singularity, we might simply need a different theory, a better projection that doesn't distort reality into meaningless infinities. And this is exactly what physicists believe. The singularity isn't considered a real, physical feature of the universe by most working physicists. It's considered an artifact of applying general relativity beyond its valid range. Something real is happening at the center of a black hole. Matter doesn't just vanish into a mathematical point. The infalling material goes somewhere and does something. But whatever that something is, general relativity can't describe it. The theory's mathematical machinery isn't equipped for that regime. This brings us to a question that might be forming in your mind. If the singularity is a breakdown, if it's a sign that the theory fails, then what would a better theory need to look like? What's missing? What ingredient is absent from general relativity that causes it to crash into infinities? The answer lies in a fundamental tension between general relativity and another pillar of modern physics, a theory that describes the universe at the smallest scales with stunning accuracy. A theory that explains how atoms work, how light interacts with matter, how the forces of nature operate at the subatomic level. A theory that, like general relativity, has never failed a single experimental test. That theory is quantum mechanics, and the singularity is the place where these two extraordinarily successful theories collide head-on. General relativity says that matter at the center of a black hole is crushed to zero volume and infinite density. But quantum mechanics says that's impossible. Quantum mechanics imposes fundamental limits on how precisely things can be localized, how tightly matter can be squeezed, how concentrated energy can become. The Heisenberg uncertainty principle, one of the bedrock principles of quantum theory, says you cannot simultaneously know the exact position and exact momentum of a particle. The more precisely you pin down where something is, the more uncertain its momentum becomes. The more you try to confine something to a smaller and smaller region, the more violently it resists. Compressing matter to a literal point of zero volume would violate this principle. Quantum mechanics doesn't allow it. So, general relativity says the matter collapses to a point. Quantum mechanics says it can't. One theory produces infinity. The other says infinity is forbidden. They directly contradict each other at the singularity. And since both theories are supported by mountains of experimental evidence, since both have passed every test ever thrown at them within their own domains, we can't simply discard one in favor of the other. We need both, and we need them to agree. They don't. Not at the singularity. not where gravity is this extreme and volumes are this small. And this disagreement, this head-on collision between the two most successful theories in the history of physics, is the deepest open problem in fundamental science. The singularity isn't just a curiosity inside a black hole. It's the arena where the foundations of physics are at war with each other. Understanding that war, understanding why general relativity and quantum mechanics refuse to cooperate at the singularity, requires us to look more closely at what each theory assumes and why those assumptions are incompatible. Because the singularity is not just telling us that general relativity is incomplete, it's telling us that something about the fundamental structure of our physical theories needs to change. And whatever that change turns out to be, it will reshape our understanding of space, time, gravity, and the nature of reality itself. We've now arrived at the core of the problem. General relativity, when followed to its logical conclusion inside a black hole, produces infinities. Density goes to infinity. Curvature goes to infinity. Physical quantities that should describe something real, instead, describe nothing at all. And we've established that these infinities aren't predictions about the universe, they're admissions of failure. They're the theory telling us it has been pushed beyond the boundary of what it can handle. But that raises an immediate question. If general relativity fails at the singularity, what theory should take over? What framework could possibly describe the conditions at the center of a black hole where matter is compressed towards zero volume and gravity is overwhelmingly strong? The answer, physicists believe, must involve quantum mechanics. And this is where the story becomes one of the deepest conflicts in all of science. Because general relativity and quantum mechanics are not just different theories about different things, they are built on assumptions that fundamentally contradict each other. And the singularity is the one place in the universe where you cannot avoid confronting that contradiction. Let me start by explaining what quantum mechanics is and why it's so successful, because you need to appreciate its power before you can appreciate the severity of the conflict. Quantum mechanics is the theory that describes the universe at the smallest scales. It governs atoms, subatomic particles, the forces that hold matter together, and the behavior of light and radiation. It was developed in the early 20th century, roughly around the same time as general relativity, and it has been tested with a precision that borders on the absurd. Consider one of its most famous predictions. Quantum electrodynamics, the quantum theory of how light interacts with matter, predicts a quantity called the anomalous magnetic moment of the electron. This is a number that describes how an electron behaves in a magnetic field. The theory predicts this number to more than 10 decimal places of accuracy, and experiments have confirmed it to more than 10 decimal places. The agreement between theory and experiment is better than 1 part in 10 billion. If you measured the distance from New York to Los Angeles with the same precision, your measurement would be accurate to within the width of a human hair. Quantum mechanics doesn't just work, it works with almost frightening precision. Quantum mechanics also gives us the physics underlying virtually all modern technology. Semiconductors, lasers, transistors, magnetic resonance imaging, nuclear energy, the chemistry of every molecule in your body. None of this would be understood without quantum mechanics. The device you're using to listen to this right now was designed using principles derived directly from quantum theory. It is, by any measure, one of the most practically successful theories ever developed. But quantum mechanics describes the universe in a way that is profoundly different from how general relativity describes it. And these differences aren't superficial. They go all the way down to the most basic assumptions each theory makes about the nature of reality. General relativity is a theory of spacetime geometry. It describes the universe as a smooth, continuous fabric that curves in response to mass and energy. This fabric has definite properties at every point. At any location and any moment, you can, in principle, specify exactly how spacetime is curved, exactly what its geometry is. The fabric doesn't jump or flicker or exist in multiple states at once. It's deterministic. Given the distribution of mass and energy, the geometry of spacetime follows uniquely from Einstein's equations. There is one answer and it is definite. Quantum mechanics is entirely different. In quantum mechanics, the world at the smallest scales is not definite. It is probabilistic. A particle doesn't have a single, exact position until you measure it. Before measurement, it exists in a superposition of multiple possible positions simultaneously. The Heisenberg uncertainty principle states that certain pairs of physical properties, like position and momentum, cannot both be precisely defined at the same time. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of your instruments. It's a fundamental feature of nature. The universe, at the quantum level, is inherently fuzzy. Quantum fields fluctuate constantly. Even in what we call a perfect vacuum, the emptiest possible region of space, quantum fields are never perfectly still. They vibrate and fluctuate, with virtual particles popping in and out of existence on timescales too short to directly observe, but with measurable physical consequences. The Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force, is direct experimental evidence of these vacuum fluctuations. The effect has been measured, and it matches the quantum prediction precisely. The vacuum is not empty. It seethes with quantum activity. Now, here is where the conflict begins. General relativity says spacetime is a smooth, continuous fabric with definite geometry. Quantum mechanics says that at the smallest scales, nothing is smooth and nothing is definite. Everything fluctuates. Everything is probabilistic. If quantum mechanics applies to everything, and there is every reason to believe it does, then it must apply to spacetime itself. Spacetime cannot be exempt from quantum rules. If matter fluctuates, if energy fluctuates, if every field we've ever studied obeys quantum mechanics, then gravity and spacetime must also obey quantum mechanics at some level. But the moment you try to apply quantum rules to spacetime, you run into catastrophic problems. In quantum field theory, the mathematical framework that combines quantum mechanics with special relativity, the fundamental forces of nature are described by fields that permeate all of space. The electromagnetic force is carried by photons, which are excitations of the electromagnetic field. The strong nuclear force, which holds atomic nuclei together, is carried by particles called gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by particles called W and Z bosons. Each of these forces has been successfully described using quantum field theory. The predictions match experiments to extraordinary precision. These quantum field theories all share a common feature. When you first write down the equations and try to calculate physical quantities, like the probability that two electrons will scatter off each other, the calculations produce infinities. This sounds terrible, and for a while it was. In the early days of quantum field theory, physicists were haunted by these divergent calculations. The theory seemed broken. But then they discovered a technique called renormalization. The idea behind renormalization is subtle and technically intricate, but the essential concept is this. The infinities that appear in the calculations can be systematically absorbed into the definitions of physical constants, like the mass and charge of the electron. You redefine these quantities to absorb the infinities, and what remains is finite, well-defined, and spectacularly accurate. The infinities were an artifact of the mathematical machinery, not a feature of nature. Once you handle them properly through renormalization, the theory gives sensible answers that match experiments perfectly. This works for electromagnetism. It works for the strong force. It works for the weak force. All three of these fundamental forces have been successfully quantized, meaning they've been incorporated into quantum field theory with renormalization, eliminating the infinities and producing finite predictions. Now try it with gravity. When physicists attempt to treat gravity the same way, writing down a quantum field theory of the gravitational field and trying to calculate physical quantities, the infinities appear again. That's expected. The infinities appeared in every other quantum field theory too. The question is whether renormalization can handle them. It can't. When you apply renormalization techniques to quantum gravity, the infinities multiply. Each time you try to absorb one infinity into a redefined constant, new infinities appear that require new constants, and those new constants generate their own infinities, requiring still more constants. The process never terminates. You need an infinite number of constants to absorb an infinite number of infinities, and the theory loses all predictive power. You can't calculate anything because every answer depends on an infinite number of unmeasured parameters. Physicists say that gravity is non-renormalizable, and this is not a technical inconvenience that might be solved with a clever mathematical trick. It is a deep structural feature of how gravity relates to quantum mechanics. The fundamental reason gravity resists quantization in the standard way comes down to what gravity actually is. In the other forces, the force-carrying particles, the photons, gluons, W and Z bosons, travel through space-time. They exist on the stage of space-time. The stage itself isn't affected by the performance. But gravity is different. Gravity is space-time. The gravitational field isn't something that exists within space-time. It is space-time. When you try to quantize gravity, you're not quantizing a field that lives on a fixed background. You're quantizing the background itself. You're trying to apply quantum rules to the very stage on which quantum mechanics is defined. Think about what this means. In standard quantum field theory, you need a space-time background to define your theory. You need a geometry to say where particles are, how they move, how fields propagate. The background is assumed to be fixed and definite. Then you put quantum fields on that background and calculate their fluctuations. But when the field you're trying to quantize is the background itself, the ground disappears beneath your feet. The framework you need to define the theory is the thing you're trying to make quantum. It's circular. It's like trying to use a ruler to measure the ruler. Here is another way to see why this is so difficult. In electromagnetism, you can ask a clear question. What is the probability that an electron at position A will scatter off a photon and end up at position B? The question makes sense because positions A and B are defined with respect to a fixed spacetime. The spacetime is the stage, and you're asking about what the actors do on that stage. But in quantum gravity, the equivalent question would be something like this. What is the probability that the geometry of spacetime transitions from one configuration to another? But what does that question even mean? You're asking about the probability of a transition, but probability requires a notion of time to define when the transition happens. And time is part of the geometry you're trying to make quantum. You can't stand outside space-time and ask about its behavior because there is no outside. There is no stage beneath the stage. Space-time is all there is. This is why the two theories are so deeply incompatible. It's not that they give slightly different answers. It's that they make fundamentally different assumptions about the nature of the arena in which physics takes place. General relativity says the arena, space-time, is a dynamic but smooth and definite geometric structure. Quantum mechanics says that at the smallest scales, nothing is smooth and nothing is definite. Both can't be right about the same regime, and for most situations in the universe, this conflict simply doesn't matter. It's completely irrelevant, because in most situations, you only need one theory or the other, never both at the same time. When you're calculating the trajectory of a satellite around Earth, you need general relativity, or at least Newtonian gravity. You don't need quantum mechanics. The satellite is a macroscopic object. Quantum effects are utterly negligible at that scale. You can safely ignore them and get the right answer using general relativity alone. When you're calculating how an electron behaves inside an atom, you need quantum mechanics. You don't need general relativity. The gravitational field inside an atom is so unimaginably weak that it has no measurable effect on the electron's behavior. You can safely ignore gravity and get the right answer using quantum mechanics alone. The two theories have, for the past century, lived in a kind of peaceful coexistence. They govern different domains. General relativity rules the large and the massive. Quantum mechanics rules the small and the energetic. Their territories barely overlap, and in the rare situations where they might overlap, like the gravitational field of a single elementary particle, the effects are so tiny that no experiment could ever detect them. The incompatibility between the two theories has been, for practical purposes, invisible, until you reach the singularity. The singularity is the one place in the known universe where peaceful coexistence ends. At the center of a black hole, general relativity says matter is compressed towards zero volume. Zero volume means incredibly tiny spatial extent. When spatial scales approach zero, you are deep in quantum territory. The uncertainty principle dominates. Quantum fluctuations become enormous. You absolutely cannot ignore quantum mechanics. It is essential. But at the same time, the gravitational field is overwhelmingly strong. The curvature of spacetime is extreme beyond anything else in the universe. You absolutely cannot ignore general relativity. It is essential. You need both theories, simultaneously, in the same place, at the same time. And the two theories refuse to cooperate. General relativity says spacetime curves smoothly all the way to a point of infinite density. Quantum mechanics says you can't squeeze matter into a point because the uncertainty principle forbids it. General relativity says the geometry of spacetime is definite and deterministic. Quantum mechanics says that at scales approaching zero, geometry must fluctuate wildly. General relativity produces infinity. Quantum mechanics says infinity is forbidden. Each theory, when applied to the singularity, gives an answer that contradicts the other. Let me make this more concrete with a thought experiment. Imagine you're trying to describe what happens to a single proton as it falls toward the singularity of a black hole. At first, while the proton is far from the center, both theories are manageable. General relativity describes the curved spacetime the proton moves through. Quantum mechanics describes the proton's internal structure, its quarks and gluons bound together by the strong force. There's no conflict, because the two descriptions operate at different scales. The curvature of spacetime changes so slowly across the tiny volume of the proton that the proton doesn't notice it. And the proton is so small that its gravitational field is utterly negligible. The two theories don't interact. But as the proton falls deeper, the curvature grows. At some point, the curvature of spacetime becomes significant across the scale of the proton itself. The geometry of space is changing dramatically over the tiny distance between one quark and another. Now, you can't separate the two descriptions. The quantum behavior of the quarks is affected by the curvature of spacetime, and the energy of the quarks affects the curvature. Gravity and quantum mechanics are coupled. You need a single, unified description that handles both simultaneously. And we don't have one. Push further. The curvature continues to grow. The proton is squeezed. Its quarks are pushed closer and closer together by the geometry of spacetime closing in around them. The quantum fields inside the proton are being compressed into an ever smaller volume. The energy associated with that compression, through the uncertainty principle, increases. The more tightly the quarks are confined, the more energetically they resist. Quantum mechanics pushes outward, gravity pulls inward, and the two forces approach a stalemate that neither theory can describe alone. Push further still. At some point, the scale of the curvature approaches the Planck length, roughly 1.6 times 10 to the negative 35 meters. This is the scale where quantum fluctuations in spacetime itself should become dominant. At this scale, it's not just that the proton exists in a strongly curved spacetime. Spacetime itself is fluctuating quantum mechanically. The stage is shaking. The geometry that general relativity treats as smooth and definite is now foaming and churning. The distinction between matter and geometry blurs. The tools of general relativity, the smooth manifold, the metric tensor, the geodesics, all assume a continuous spacetime that simply doesn't exist at this scale. And the tools of standard quantum field theory assume a fixed spacetime background on which fields fluctuate. But there is no fixed background here. The background is itself quantum. This is the Planck scale, and it's where the known laws of physics exhaust themselves completely. Not approximately, not partially, completely. To understand why the Planck scale is so special, consider where it comes from. The Planck length is not an arbitrary choice. It's the unique length scale you can construct by combining three fundamental constants of nature: the speed of light, which is the foundation of relativity and sets the cosmic speed limit; Newton's gravitational constant, which measures the strength of gravity; and Planck's constant, which sets the scale of quantum effects. When you combine these three numbers, the only length you can build from them is the Planck length. It's the scale where relativistic effects, gravitational effects, and quantum effects all become simultaneously important. It's the scale where the three pillars of modern physics collide. At distances much larger than the Planck length, general relativity works perfectly and quantum gravity effects are negligible. At the Planck length, they are not negligible, they dominate. And since we don't have a theory that correctly handles all three regimes simultaneously, we have no reliable description of physics at this scale. The singularity, according to general relativity, is a point, a zero-dimensional location, smaller than the Planck length, smaller than any length, infinitely small. This means the singularity is deep within the regime where quantum gravity effects should dominate. It's not at the edge of our ignorance, it's at the very center of it. This is why physicists believe that a proper theory of quantum gravity would resolve the singularity. Not just describe it differently, but eliminate it entirely. The infinite density and infinite curvature that general relativity predicts are artifacts of pushing a classical theory, a theory that doesn't account for quantum effects, into a regime where quantum effects are the dominant feature of reality. If we had a theory that properly incorporated both gravity and quantum mechanics, the expectation is that the singularity would be replaced by something finite. Something strange, probably. Something we've never seen or imagined, possibly. But something with definite, finite physical properties. Not infinity. Let me explain why this expectation is reasonable by looking at how quantum mechanics has resolved other classical infinities. Go back to the atom. In classical physics, the model of an atom with electrons orbiting a nucleus has a catastrophic problem. An accelerating charged particle radiates energy. An electron orbiting a nucleus is constantly accelerating because it's constantly changing direction. So it should radiate energy, lose speed, spiral inward, and crash into the nucleus in a fraction of a second. Every atom in the universe should be unstable. Matter shouldn't exist. This is a kind of classical singularity. The electron spirals in, the energy radiated goes to infinity, and the system collapses. Classical physics predicts a catastrophic outcome that doesn't match reality. Quantum mechanics resolves this beautifully. The electron isn't a little ball orbiting the nucleus on a definite path. It exists as a quantum probability cloud, a wave function spread over a region of space. The uncertainty principle prevents the electron from collapsing into the nucleus. If the electron were localized to a very small region near the nucleus, its position would be very precisely defined, but then its momentum would become enormously uncertain, meaning it would have a huge kinetic energy that would push it outward. There's a balance, a ground state, a minimum energy configuration below which the electron cannot fall. The atom is stable. The classical infinity is avoided because quantum mechanics introduces a minimum scale, a floor below which the system cannot collapse. Physicists expect something similar might happen at the singularity. The classical prediction is that matter collapses to a point of zero volume. But if quantum gravity introduces a minimum meaningful length, like the Planck length, then the collapse would stop. Matter couldn't be compressed below a certain scale. Density would reach a maximum finite value, extraordinary by any standard, but finite. The singularity would be resolved. This is not a confirmed result. Nobody has proven this. We don't have a complete theory of quantum gravity, so we can't calculate what actually replaces the singularity. But the pattern from the history of physics is strongly suggestive. Every time classical physics has predicted an infinity, quantum mechanics has resolved it by introducing a minimum scale or a ground state. The atom didn't collapse. The ultraviolet catastrophe of black-body radiation didn't produce infinite energy. The vacuum didn't have infinite electromagnetic energy. In every case, quantum effects stepped in at small scales and turned infinity into something finite. The singularity is widely expected to follow the same pattern. General relativity, a classical theory with no quantum effects, predicts infinite curvature. A quantum theory of gravity should introduce effects that prevent curvature from actually reaching infinity, just as quantum mechanics prevents the electron from crashing into the nucleus. But here is what makes the singularity problem so much harder than these earlier examples. In every previous case, the solution involved quantizing fields on a fixed spacetime background. You keep spacetime smooth and continuous, and apply quantum rules to the matter and energy living on it. The background stays classical, only the content becomes quantum. At the singularity, this approach fails because the background itself is the thing that's blowing up. Spacetime is the field that's producing the infinity. You can't treat spacetime as a fixed stage and quantize everything else, because the stage is the problem. You need to quantize the stage. You need a quantum description of spacetime itself. And this is something no established theory provides. The technical difficulty is staggering. In standard quantum field theory, space and time provide the scaffolding for the entire mathematical framework. Positions of particles are defined relative to spacetime. The evolution of quantum states is defined with respect to time. Probabilities are calculated over spatial regions. If spacetime itself becomes quantum, if it fluctuates, if it doesn't have a definite geometry, then what does it mean to specify a position? What does it mean for a system to evolve in time if time itself is not well defined? How do you calculate probabilities when the space over which you're integrating is itself in a quantum superposition? These aren't small questions. They strike at the mathematical foundations of quantum theory. Answering them requires not just new equations, but potentially new mathematical structures, new ways of thinking about what a physical theory even is. This is why the problem of quantum gravity has resisted solution for nearly a century. It's not that physicists haven't tried. Thousands of brilliant researchers have devoted their careers to this problem. The difficulty is intrinsic. The two theories are built on incompatible foundations, and merging them requires rebuilding at least one of those foundations from the ground up. And the singularity sits at the center of this incompatibility. It's not just an abstract puzzle for theorists. Real black holes exist. There are billions of them in our galaxy alone. Sagittarius E star, the supermassive black hole at the center of the Milky Way, has a mass of about 4 million times the mass of our Sun. The black hole at the center of M87 has a mass of about 6.5 billion solar masses. We've detected gravitational waves from dozens of black hole mergers. Black holes are among the most common large-scale structures in the universe, and every single one of them, according to general relativity, contains a singularity at its center. Every one of them contains a region where our two most fundamental theories of nature give contradictory answers. Every one of them is a physical laboratory for conditions we cannot describe. The singularity isn't an academic problem. It's a real gap in our understanding of objects that actually exist. The universe contains countless regions where physics, as we currently understand it, stops working. That's not a small thing. That's not a footnote. That's a crisis in the foundations of modern physics. And the only way to resolve it is to find the theory that unifies gravity with quantum mechanics. A theory of quantum gravity. The missing piece that would tell us what actually happens where general relativity breaks down. That theory is the greatest unsolved problem in fundamental physics. It has been sought for almost 100 years. The greatest minds in theoretical physics have worked on it, and while several promising approaches have been developed, none has been confirmed. None has made a prediction that we can test with current technology. The singularity remains unresolved, but the search itself has produced extraordinary ideas about the nature of space, time, and reality. Ideas that challenge everything we think we know about the universe. Ideas about what might replace the singularity, about whether space-time itself has a deeper structure, about whether the infinite values in general relativity are hiding something entirely new beneath them. So, the singularity marks the place where general relativity and quantum mechanics collide. It's the one location in the universe where neither theory alone can provide a description that makes physical sense. General relativity produces infinity. Quantum mechanics forbids infinity. The two frameworks contradict each other at the deepest possible level, and resolving this contradiction requires something entirely new. A theory that doesn't yet exist in its final form. A theory that would describe gravity and space-time using quantum principles. A theory of quantum gravity. But what would such a theory actually need to do? What would it need to explain? And what clues do we have about what it might look like? The first and most fundamental requirement is that a theory of quantum gravity must eliminate the singularity. Not by ignoring it, not by waving it away, but by providing a physical description of the region where general relativity currently produces infinite values. The infinite density, the infinite curvature, the geodesic incompleteness. All of these must be replaced by something finite, something calculable, something physically meaningful. Whatever is really happening at the center of a black hole, a quantum theory of gravity must be able to describe it. The second requirement is that the new theory must reproduce all the successes of general relativity in the regimes where general relativity already works. This is crucial. General relativity hasn't failed in any experiment. It hasn't gotten any prediction wrong. It describes gravitational lensing, gravitational time dilation, gravitational waves, the behavior of binary pulsars, the shadows of black holes, all of it with extraordinary precision. Any replacement theory must agree with general relativity in all these domains. It must reduce to Einstein's equations in the appropriate limit, the way Einstein's equations reduce to Newton's law of gravity when gravity is weak and speeds are slow. The new theory can't just fix the singularity. It must fix the singularity while preserving everything else. The third requirement is that the theory must be internally consistent as a quantum theory. It must obey the principles of quantum mechanics: superposition, uncertainty, the probabilistic structure of measurement, the unitarity of time evolution, which essentially means that information must be conserved. Whatever replaces space-time geometry at the Planck scale must be quantum in nature, and the theory describing it must be mathematically coherent. These requirements are extraordinarily demanding, and meeting all of them simultaneously is what makes quantum gravity the hardest problem in theoretical physics. Let me talk about the scale at which quantum gravity effects should become important, because understanding this scale helps explain both why the singularity is a problem and why the problem is so hard to solve experimentally. The Planck length, roughly 1.6 times 10 to the negative 35 meters, is the distance scale where quantum gravitational effects should dominate. To give you a sense of how small this is, consider that a proton, which is already far too small to see with any optical device, has a diameter of about 10 to the negative 15 meters. The Planck length is about 20 orders of magnitude smaller than a proton. If you could magnify a proton to the size of the observable universe, the Planck length would still be smaller than a millimeter. This extreme smallness is also why the problem is so hard to approach experimentally. To directly probe physics at the Planck scale, you would need a particle accelerator capable of reaching the Planck energy, about 10 to the 19 billion electron volts. Our most powerful accelerator, the Large Hadron Collider, reaches about 10 to the 13 electron volts. That's roughly a quadrillion times too weak. Building an accelerator powerful enough to reach Planck energy would require a machine larger than the solar system. It's not just beyond current technology, it's beyond any technology conceivable within the known laws of physics and engineering. We cannot brute force our way to quantum gravity through sheer experimental power. This means that the singularity problem must be attacked primarily through theory and through indirect observations. We need mathematical frameworks powerful enough to predict what happens at the Planck scale, even though we can't reach that scale in a laboratory. And we need creative ways to find observational signatures of quantum gravity effects that might be visible at accessible energies. At distances much larger than the Planck length, spacetime behaves as a smooth, continuous fabric, exactly as general relativity describes. Quantum fluctuations in the geometry of spacetime exist at all scales, but at distances well above the Planck length, those fluctuations are so unimaginably tiny that they have no measurable effect on anything. It's like the surface of a calm ocean. Zoom out far enough, and the surface looks perfectly smooth. But zoom in to the molecular scale, and you'd see individual water molecules jostling and vibrating chaotically. The ocean is smooth at large scales, and turbulent at small scales. Spacetime may be the same, smooth at the scales we can observe, turbulent and quantum at the Planck scale. As you approach the center of a black hole, the curvature of spacetime grows. At some point, the curvature becomes so extreme that the scales involved shrink to the Planck length. This is where quantum gravity effects can no longer be ignored. This is where general relativity's smooth description of spacetime must give way to something quantum. The singularity, in general relativity, is a point where curvature reaches infinity. But if quantum gravity introducing a minimum meaningful length, if spacetime has a granular structure at the Planck scale, then curvature might not be able to reach infinity. It would reach some maximum finite value, the Planck density of about 10 to the 96 kilograms per cubic meter. Extraordinary, but finite. The singularity would be replaced by a region of extreme but bounded curvature. This is the expectation. But turning this expectation into a concrete, testable prediction requires a complete theory. And that's where the candidate frameworks come in. Two major approaches have been developed over the past several decades. They take very different philosophical and mathematical paths, and they arrive at different pictures of what might replace the singularity. Neither has been confirmed experimentally, but both offer deep insights into how quantum gravity might work. The first is string theory. String theory proposes that the most fundamental building blocks of the universe are not point particles, but tiny, one-dimensional objects called strings. These strings are roughly the Planck length long, far too small to observe directly. Different vibration patterns of these strings correspond to different types of particles. One vibration pattern gives you an electron, another gives you a quark, another gives you a photon, and crucially, one vibration pattern naturally corresponds to a graviton, the hypothetical particle that carries the gravitational force. This is one of string theory's greatest achievements. In standard quantum field theory, when you try to include gravity by introducing a graviton as a point particle, the calculations produce uncontrollable infinities. Gravity is non-renormalizable. But in string theory, because the fundamental objects are extended strings rather than points, the interactions are smeared out over a tiny but non-zero length scale. This smearing eliminates the infinities. The calculations that blow up for point particles converge for strings. String theory is a mathematically consistent quantum theory that includes gravity from the start. It doesn't struggle to incorporate gravity. Gravity emerges from it naturally. For the singularity, string theory suggests a resolution rooted in the extended nature of strings. A point particle can be compressed to zero volume because it has no spatial extent. But a string cannot be compressed below its own length. It has a minimum size. This minimum size acts as a natural cutoff, preventing the kind of infinite compression that general relativity predicts at the singularity. The singularity in string theory might be resolved simply because the fundamental objects of the theory cannot be squeezed to a point. The mathematics won't allow it. The very structure of the theory forbids the kind of zero-volume, infinite density configuration that constitutes a singularity. There's a deeper aspect to this. In string theory, there is a principle called T-duality that relates physics at very small scales to physics at very large scales. If you try to compress a string below a certain length, the physics doesn't become more extreme. It becomes equivalent to physics at a larger scale. Very small and very large become mirrors of each other. This means there is effectively a minimum distance in string theory. You can't probe below it because below it just looks like above it. The singularity, which requires reaching zero distance, becomes physically inaccessible. Not because something stops you, but because the concept of going smaller ceases to make sense within the theory. Some string theory calculations suggest that the interior of a black hole might be replaced by a structure called a fuzzball. In the fuzzball picture, the black hole isn't a region of empty curved spacetime with a singularity at the center. Instead, the entire interior is filled with a complicated configuration of strings and higher dimensional objects called branes. There is no empty space inside. There is no singularity. The boundary of the fuzzball corresponds to the event horizon, but its interior is a quantum object with finite, well-defined properties. The infinite density point is replaced by a distributed quantum structure. The mass of the black hole isn't concentrated at a point. It's spread throughout the interior, encoded in the complex configurations of strings and branes. However, string theory comes with complications. To be mathematically consistent, string theory requires extra spatial dimensions beyond the three we experience. Depending on the version, the theory requires 9 or 10 spatial dimensions plus 1 time dimension, totaling 10 or 11 dimensions. The extra dimensions, if they exist, must be compactified, curled up at the Planck scale into shapes too small to detect directly. The geometry of these extra dimensions, often described as Calabi-Yau manifolds, determines the properties of particles and forces in our observable universe. This is both powerful and problematic. It's powerful because it means the properties of our universe, the masses of particles, the strengths of forces, might ultimately be explained by the geometry of hidden dimensions. It's problematic because there are an enormous number of possible geometries. Estimates suggest roughly 10 to the 500 different configurations, each giving rise to a different set of particles and forces. Which one describes our universe? Without experimental data from the Planck scale, we can't determine this. The theory has a vast landscape of possibilities, and we lack the means to narrow it down. The second major approach is loop quantum gravity, where string theory replaces point particles with strings and works in extra dimensions. Loop quantum gravity takes a more conservative route. It stays in the 4 dimensions we experience, 3 of space and 1 of time, and attempts to directly quantize the geometry of spacetime itself. It takes general relativity seriously as a starting point and asks a straightforward question. What happens when you apply quantum rules directly to the geometry of space? The core idea of loop quantum gravity is that space is not a smooth, continuous fabric. It has a discrete structure at the Planck scale. Area and volume come in quantized chunks, just as energy comes in quantized packets in ordinary quantum mechanics. There is a smallest possible area, proportional to the Planck length squared. There is a smallest possible volume, proportional to the Planck length cubed. Space is granular. Below the Planck scale, there is no more space to probe. The concept of distance shorter than the Planck length simply doesn't exist in this framework. The mathematical structure of loop quantum gravity is built on objects called spin networks. A spin network is a graph, a collection of nodes connected by links. The links carry labels related to area, and the nodes carry labels related to volume. Different configurations of the spin network correspond to different geometries of space. Space, in this picture, isn't a smooth backdrop. It's a quantum state of a network, a web of discrete relationships. At large scales, when you have an enormous number of nodes and links, the network looks smooth and continuous, just as general relativity describes. The way a digital photograph looks smooth when you view it from normal distance, even though it's made of discrete pixels. But at the Planck scale, the discreteness becomes apparent. You see the pixels, you see the graininess. You encounter the fundamental building blocks from which smooth spacetime is assembled. For the singularity, loop quantum gravity offers a specific and striking prediction. Because there is a minimum meaningful volume, matter cannot be compressed to a point. When collapsing matter reaches Planck density, the quantized geometry of space generates a repulsive pressure. This isn't thermal pressure or radiation pressure or any form of pressure we encounter in ordinary physics. It's a purely geometric effect that arises from the discrete quantum structure of spacetime itself. It only becomes significant at extreme densities approaching the Planck scale. In everyday physics, it's completely undetectable. But when densities approach the Planck density, this quantum geometric pressure becomes the dominant force. And when it does become significant, it halts the collapse. In loop quantum cosmology, which applies the principles of loop quantum gravity to the universe as a whole, this mechanism resolves the Big Bang singularity. Instead of the universe beginning at a point of infinite density, the universe underwent a quantum bounce. A previously contracting universe reached Planck density. The quantum geometric pressure kicked in, and the contraction reversed into expansion. The Big Bang, in this picture, wasn't the beginning of everything. It was a transition, a bounce, from a contracting phase to an expanding phase. Time didn't begin, it continued through the bounce, linking our expanding universe to whatever came before. Some researchers have applied similar reasoning to black hole singularities. If quantum geometry prevents infinite compression, then the center of a black hole might not contain a singularity. Instead, the collapsing matter might reach Planck density and bounce, possibly creating a new expanding region of spacetime. Some models suggest this could form a white hole, a time reverse of a black hole that expels matter rather than swallowing it. Others suggest the bounce might create a baby universe, a new region of spacetime connected to ours only through the black hole interior. These ideas remain speculative. They depend on calculations within a framework that is still under development. But they demonstrate how quantizing spacetime geometry could resolve the singularity by introducing a minimum scale that prevents infinite compression. Both string theory and loop quantum gravity also connect to one of the deepest puzzles in black hole physics, the black hole information paradox. In 1974, Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit thermal radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly lose mass. Over immense timescales, a black hole should eventually evaporate completely, disappearing entirely. The process is extraordinarily slow. A black hole with the mass of our Sun would take roughly 10 to the 67 years to evaporate. That's trillions of trillions of trillions of times longer than the current age of the universe. Supermassive black holes would take even longer. But the important point isn't the timescale. The important point is that black holes, in principle, are not permanent. They have a finite lifetime. They eventually disappear. And that disappearance creates a problem. The Hawking radiation is thermal. It appears to be random, carrying no information about what fell into the black hole. If a black hole evaporates completely and the radiation carries no information, then the information about everything that ever fell in is permanently destroyed. A book, a star, a person, all the information describing these objects would be gone forever. The radiation tells you the temperature of the black hole. It tells you its mass, but it tells you nothing about what the black hole was made of. A black hole formed from the collapse of a star made entirely of iron would emit the same Hawking radiation as a black hole formed from the collapse of a star made of hydrogen. The specific information about the initial state would be erased. This violates a fundamental principle of quantum mechanics: unitarity. In quantum mechanics, information is never destroyed. The evolution of a quantum system is always reversible in principle. You can always, in theory, reconstruct the initial state from the final state. If you know the complete quantum state of a system at one time, you can calculate what it was at any earlier time. Information is scrambled, rearranged and distributed, but never erased. If a black hole destroys information, quantum mechanics is wrong. If quantum mechanics is right, the information must somehow survive. This is directly connected to the singularity. If the singularity is real, if matter truly vanishes into a point of infinite density, then perhaps information really is destroyed there. The singularity would be a place where quantum mechanics breaks down. But most physicists believe quantum mechanics doesn't break down. They believe the information is preserved somehow, encoded in subtle correlations in the Hawking radiation, or stored in the quantum structure that replaces the singularity. Resolving the singularity and resolving the information paradox may ultimately be the same problem, two faces of the same underlying mystery. Jacob Bekenstein showed in the early 1970s that a black hole's entropy, a measure of how much information it contains, is proportional to the area of its event horizon, not its volume. This was a revolutionary insight. In every other physical system we know, entropy scales with volume. A box twice as big can contain twice as much entropy. A room with twice the volume can hold twice as many possible arrangements of its contents. But for black holes, entropy scales with surface area. This is deeply strange. It suggests that the information about everything inside a black hole is somehow encoded on its two-dimensional boundary, the event horizon, rather than being distributed throughout its three-dimensional interior. Think about how counterintuitive this is. Everything that has ever fallen into a black hole, all the stars, all the gas, all the matter with all its complex structure and information, all of that information is encoded not in the volume of the black hole, but on its surface. It's as if the contents of a room were fully described by what's written on its walls. The interior is redundant. The boundary contains everything. This idea eventually developed into the holographic principle, one of the most profound concepts in modern theoretical physics. The holographic principle states that the maximum amount of information that can be contained in any region of space is proportional to the area of the boundary of that region, not its volume. Just as a hologram encodes three-dimensional information on a two-dimensional surface, the physics of a volume of space might be entirely encoded on its boundary. If the holographic principle is correct, it changes what we mean by a singularity. The infinite density at the center might be an artifact of trying to describe three-dimensional physics in 3 dimensions, when the true description is fundamentally two-dimensional. The singularity might not be a place where physics breaks. It might be a place where the wrong description is being applied. A holographic description, formulated on the boundary, might be perfectly well defined even where the bulk description, formulated in the interior, fails. The most concrete realization of the holographic principle is the ADS-CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997. This correspondence relates a gravitational theory in a certain kind of curved spacetime to a quantum field theory without gravity, living on the boundary of that spacetime. The two theories are different descriptions of the same physics. Every question you can ask in the gravitational theory has an equivalent formulation in the boundary theory, and vice versa. They are two languages for the same physical reality. Remarkably, the boundary theory is completely well defined. It has no singularities. It's a standard quantum field theory with finite, calculable answers. And yet it encodes all the information about the gravitational physics in the interior, including black holes. In the boundary theory, a black hole corresponds to a thermal state, a hot soup of quantum particles at a specific temperature. There is no singularity in the boundary description. The physics is perfectly smooth. The information about what fell into the black hole is preserved, scrambled among the thermal degrees of freedom on the boundary, but not destroyed. This suggests that the singularity in the interior is an artifact of the gravitational description, not a feature of the underlying physics. If you describe the same system using the boundary theory, the singularity never appears. The physics is finite. The information is conserved. Everything that general relativity couldn't describe is handled smoothly by the boundary theory. This is one of the strongest hints we have about how quantum gravity might resolve the singularity. The duality tells us that there exists a description of black hole physics that is completely singularity-free. The singularity is a feature of one mathematical language, the language of classical space-time geometry, but it disappears when you translate the same physics into a different, more fundamental language. Just as the Mercator projection's singularity at the poles disappears when you switch to a different projection, the black hole singularity might disappear when you switch to the right theoretical framework. Now, let me be clear about the current state of affairs. We do not have a complete theory of quantum gravity. Neither string theory nor loop quantum gravity has been experimentally confirmed. Neither has produced a definitive, testable prediction that distinguishes it from general relativity in a regime we can currently probe. The ADS-CFT correspondence applies to a type of space-time with a negative cosmological constant, which is not the kind of universe we live in. Our universe has a positive cosmological constant. Extending the lessons of the correspondence to our universe remains a major open problem. But the convergence of different approaches is striking. String theory, loop quantum gravity, and holographic arguments all point in the same direction. The singularity is not real, it's an artifact. Something finite and well-defined replaces it. The specific details differ between frameworks. String theory points to fuzzballs, or extended string configurations. Loop quantum gravity points to quantum bounces and maximum density. Holography points to boundary descriptions that are intrinsically singularity-free. But the conclusion is shared. The singularity marks the boundary of general relativity's validity, not the boundary of physical reality. And yet, the singularity remains unresolved. We have strong theoretical reasons to believe it will be resolved. We have candidate frameworks that show how resolution might work, but we don't have proof. We don't have a confirmed theory. We don't have experimental evidence that any of these candidate frameworks accurately describes what happens at the Planck scale. The singularity is still an open question. Perhaps the most important open question in all of physics. Why does this matter? Why should anyone care about what happens at the center of a black hole, behind an event horizon, in a region that no observation can ever reach? It matters because the singularity is not just about black holes. The singularity is a stress test for the foundations of physics. It is the specific, concrete, physically real situation where the two deepest theories of nature contradict each other. General relativity and quantum mechanics are the two pillars on which all of modern physics rests. Every prediction we make about the universe, from the behavior of atoms to the expansion of the cosmos, relies on one or both of these theories. And they don't agree. They give contradictory answers about a situation that the universe actually produces. That's not a minor inconsistency. That's a crack in the foundation. Resolving the singularity means finding the theory that sits beneath both general relativity and quantum mechanics. It means discovering the deeper framework from which both theories emerge as approximations. It means understanding the true nature of spacetime, whether it's continuous or discrete, whether it's fundamental or emergent, whether the concepts of space and time that we take for granted are the bedrock of reality or just effective descriptions that break down at extreme scales. This deeper theory would answer questions far beyond what happens inside black holes. It would tell us what happened at the very beginning of the universe, in the first Planck time after the Big Bang, when the entire observable cosmos was smaller than a Planck length and quantum gravity effects dominated. It would tell us whether our universe had a true beginning, or whether it emerged from a previous state through a quantum bounce. It would tell us whether the constants of nature, the masses of particles, the strengths of forces, are fixed by the theory or are environmental, varying from one region of a larger multiverse to another. It would potentially unify all four fundamental forces of nature into a single framework, completing a quest that has driven physics for over a century. The singularity is the clearest signpost pointing toward all of this. It is the most concrete, the most specific, the most unavoidable demonstration that our current understanding is incomplete. You cannot look at the singularity and conclude that physics is finished. You cannot encounter a place where your best theory produces infinity and believe you've reached the end of knowledge. The singularity doesn't close a door, it opens one. It tells us there is something beyond what we currently know, something deeper, something more fundamental, something that, when we finally discover it, will change our understanding of reality as profoundly as Einstein changed Newton's. And this is perhaps the most remarkable thing about the singularity. It is a place where physics breaks, and yet it is also a place that points toward the next revolution. The history of physics is a history of breakdowns leading to breakthroughs. The failure of classical mechanics at high speeds led to special relativity. The failure of classical physics at atomic scales led to quantum mechanics. The failure of Newtonian gravity in strong fields led to general relativity. Each time a theory broke, a deeper theory was waiting behind it. The breakdown was never the end of the story. It was the beginning of a new chapter. The singularity is the next breakdown. It is general relativity telling us, in the most dramatic way possible, that there is a deeper chapter waiting to be written. We don't know what that chapter will say. We don't know when it will be written. The problem has resisted the efforts of the greatest physicists for almost a century. But every candidate framework, every theoretical advance, every new piece of mathematics developed in the quest for quantum gravity brings us incrementally closer. Somewhere at the center of every black hole in the universe, in a region hidden behind an event horizon, sealed off from observation by the very curvature of spacetime, something is happening that we cannot yet describe. Matter is being compressed to densities we have no theory to calculate. Spacetime is curving to extremes we have no framework to handle. The deepest laws of nature are being tested in ways we cannot observe, and those laws, we already know, are failing. Not because the universe is broken, but because our understanding of the universe is still incomplete. The singularity is not the end of the story. It is the place where the story we've been telling, the story of smooth spacetime curving under the influence of mass and energy, the story that general relativity has told so successfully for over a century, finally reaches a sentence it cannot finish. The theory drives toward the center of the black hole, producing numbers that grow and grow, curvature climbing, density rising, tidal forces mounting, until the numbers pass all physical meaning and reach infinity. And at that point, the theory falls silent. Not because there's nothing more to say, but because it doesn't have the language for what comes next. Quantum mechanics doesn't have that language either, not in its current form. The two theories stand on opposite sides of the singularity, each holding a piece of the answer, each unable to cross the gap alone. General relativity describes the gravitational collapse that creates the conditions. Quantum mechanics imposes the limits that should prevent the infinity. But neither can complete the picture without the other, and they don't know how to work together. Not yet. What we need is the theory that bridges the gap, the theory that speaks both languages, the language of curved geometry and the language of quantum uncertainty, and weaves them into a single, coherent description. That theory will tell us what actually happens where general relativity predicts a singularity. It will replace infinity with something finite. It will complete the sentence that general relativity cannot finish. And when it does, when that theory is finally found, it won't just solve the singularity problem. It will reveal what spacetime really is. Not the smooth, continuous fabric that Einstein described, beautiful and powerful as that description is, but whatever deeper structure lies beneath. The structure from which spacetime emerges. The structure that explains not just how gravity works, but what gravity is at the most fundamental level. The structure that connects the quantum world of particles and fields to the geometric world of curvature and horizons. That is what the singularity means. Not a point of infinite density at the center of a black hole. Not a place where the universe does something impossible. The singularity is a boundary. The boundary where the deepest known laws of physics stop agreeing. The boundary where the most successful theory of gravity reaches the limit of what it can describe. The boundary beyond which something new, something we haven't discovered yet, governs the behavior of space, time, matter, and energy. Every black hole in the universe contains this boundary. Every one of them is a laboratory for conditions we cannot describe, and every one of them is a reminder that our understanding of the universe, as extraordinary as it is, still has a frontier. The singularity is that frontier, and the most important discoveries in physics may be waiting on the other side.